In this video, we're going to talk about the polarity of molecules. So the question is why don't oil and water mix? If I have a container and I pour water into it, if I come through and I add oil to it, which will be the red coloration here, it floats on top. They don't mix. But why? The answer lies at the molecular level. Here we have a typical oil molecule. There's a long chain of carbon and hydrogen atoms. And this chain can actually bunch up kind of like that. Now, water are singular molecules. They're very small. There's an oxygen at the top and two hydrogens. Now, when we have an aggregate of water, they actually align themselves up much like the oil chain does. And you'll see that the hydrogens are attracted to oxygens on adjacent molecules and vice versa. So might that have something to do with why oil and water don't mix? The top video is going to show us water molecules if they were attracted to another water molecule. So if you watch, as other water molecules come close to these molecules, they start to arrange themselves, hydrogen to oxygen, and so on and so forth. There is an attraction between the molecules, and that is why they're moving around and they form this sort of strange chain. Now, if we have an oil molecule, which in the bottom video is going to be played by the gray and white spheres, look what happens when water comes near them. It doesn't arrange itself, it doesn't move like the water molecules did. Now, why is this? It is because the polarity of the oil molecule is different than that of the water. So the shape of the molecule helps to determine the polarity. And we can tell if a bond is polar based upon electronegativity. The electronegativity is a measure of how strongly an atom pulls a shared pair of electrons toward itself. Now, oxygen is very electronegative. It pulls electron density away from the hydrogens toward itself, which makes the oxygen a little bit more negative, and it makes the hydrogens a little bit more like positive. And you can think of this in terms of a magnet. This has got two poles, what we call a dipole. The higher the electronegativity difference, the more polar the bond. And you can see we have some values of electronegativities for the main group elements, but there is a periodic trend to this. As you go across a period, the electronegativity increases. And as you go up a family, the electronegativity increases until you hit fluorine, which is the most electronegative element on the periodic table. Fluorine basically tries to steal electrons no matter what the cost. It will try to take electrons from anything. It would try to take electrons from a puppy. Fluorine is that electronegative. Now, if you take a look at the difference between, say, carbon and hydrogen, it's a small difference. This would be what we call a non-polar covalent bond. It doesn't have a pole. But from oxygen to hydrogen, 3.5 to 2.1, this is a polar covalent bond. The oxygen is going to be more negative. Not a true full-on negative, and the hydrogen is not a true full-on positive. It's what we call a delta negative and a delta positive. The lowercase Greek delta just means a small amount. So a small amount of negative and a small amount of positive. Now, in order for a molecule to be polar, it must have a polar bond. And it must have a shape that allows the polarity to reinforce. So with water, you can see we have another way that we can show the dipole, the arrow with a positive little slash toward the positive end, and the arrowhead pointing toward the negative end. When these two arrows point together, they give you what is called a net dipole moment. In other words, water molecule behaves like a tiny bar magnet. Now, symmetry is important. Molecules with a high degree of symmetry tend to be nonpolar because they start to cancel out their dipoles. So, for example, carbon tetrachloride. The carbon to chlorine bond is very polar. However, the dipoles actually in 3 dimensions cancel each other out. So we have one chlorine going up, one chlorine going to the side, one chlorine coming out, and one chlorine going back. They all cancel each other out, and the effect is that we end up with a non-polar molecule. If you want to learn more about polarity, you can go to Mark Bishop's site, which is a virtual textbook on the introduction to chemistry. The link is here, and his stuff on molecular polarity is very good. He gives us a lot of examples. So I hope you enjoyed this video on polarity, and now you know why oil and water don't mix.